We are live. Okay. Are we live? Let me check a couple things. Yes, we are. All right. 1, 2, 3. Good morning, everyone. How's everybody doing? All right. I am very happy today to announce that we have a guest lecture. We have the second guest lecture of the semester with Maria Yablonina. All right. I'm just a little bit of infrastructure. The way this works is as usual. We are right now on a private Zoom call with participants only from the class, the Introduction to Computational Design course here at the Harvard Graduate School of Design. However, we're also streaming this lecture live to YouTube, and I am actually monitoring right now the chat. We have about 35 participants. So I would like to make this lecture as participatory for everyone as possible. So people in the call in Zoom will be encouraged to participate, as well as people on YouTube right now. When we open up to questions, you will also be welcome to post your questions on the chat, and I will relay them to Maria. Okay. And I would like to introduce Maria. Maria is an architect, is a designer, is an artist, is so many things. I'm fascinated by her work constantly. We met, where we went, like 4 years ago, 5 years ago, in a doctoral workshop.
Something, yeah,
like that.
I think
Yeah.
so.
And I was immediately fascinated by the quality, the depth, and the novelty of a lot of the things that she was already doing back in the times and everything that came afterwards. She has been working consistently and coined a term, designing with machines, because a lot of her work involves thinking about how mechanical artifacts, machines, robots in many different forms can help us be more creative and how we can use them to advance what we do as designers and creative people. I'm very happy that she accepted the invitation to be here today with us. And I'm also super excited because she has like something very special prepared for the lecture today, which I'm not going to disclose. And I'm actually going to shut up and stop talking, and I'm going to give her the stage right now. Okay. Thanks a lot, Maria, and welcome.
Thank you so much. Thank you for the lovely introduction. I can't believe it's been that long. It's crazy. So I'm going to quickly start sharing my screen. I'm not going to share computer sound in case if I haven't muted any videos. So before I actually start talking, I would like to kind of tell you about how I want to structure this lecture today. It's something new for me, and I'm hoping new for you as well. So I call this format Choose Your Own Adventure Lecture. So basically what I have currently opened on my computer is a giant slide deck that we're not going to be able to go through within the time that we have. But the idea is that the slide deck is separated into different chunks or snippets, as I call them. And every snippet, some are about my own work, some are about the work that I love, some are about some history, about machines and architecture, etc., and brief history of mobile robots. So I'm now going to start with an introduction snippet, which you don't get to choose. But once I'm done with that, it's going to be up to our Zoom audience to vote on which snippet comes next. So theoretically, there's kind of a flow of how this goes that is briefly described in these arrows, but you're totally free to jump and kind of force myself into a situation where I have to like switch my brain gears from talking about projects to talking about history, which is always very exciting. And I'm hoping that you're going to enjoy it. I'm hoping that I'm going to enjoy it. And then we'll see how it goes. Cool. So as you've already heard from the introduction, my name is Maria. I'm an assistant professor at the Daniels Faculty of Architecture, Landscape and Design, and a member of the Robotics Institute at the University of Toronto. I'm an architect and researcher working in the field of computational design, digital fabrication, and specifically focusing on architectural robotics. Super happy to be here and have this opportunity to share my work with you. And generally my approach to robotics and automation in architecture that I refer to as designing with machines. So I'm going to start this conversation or this lecture, I like to frame it as a conversation, with the notion of a robot itself, or if you will, a notion of a machine in architecture. The relationship between machine design and architectural design practices is of course not new and has taken many, many forms. starting from speculative visions of architectural futures, where the boundary between the architectural space and the machine becomes very blurred, to then prototypes of intelligent buildings that are capable not only of mechanical movement, but also some level of intelligent response, some level of decision-making, and oftentimes even boredom. And then, of course, on the other hand, we have the construction automation boom that has been happening for quite a bit now, where the agenda is not necessarily to explore robotically actuatable and machine-like spaces, but really to focus on conventional construction and fabrication processes that can be automated and then performed by teleoperated, or in some cases, autonomous machines. In contrast to that, the field of architectural research that I find myself in and that I have been kind of a community member of for the past years, not sure how many now, has a very different approach to automation, where the aspiration is not to merely optimize an existing process, but really to explore new materials, methods, and ultimately an entirely new design space that is enabled by technology. And of course, a major role in this undertaking is played by an industrial robotic arm, which we're now, I guess, very used to seeing in both architectural schools, architectural projects, and oftentimes in architectural practices. And this machine, this particular type of machine body, has become almost synonymous and almost kind of a symbol and an icon of computational design and digital fabrication and architecture. However, while this appropriation of an industrial machine into architecture has been incredibly productive, we've seen so many different new processes, so many new different materials used for architecture that were not possible before, we also have to be very critical and acknowledge the limitations that these particular types of machine bodies place us in. And of course, these limitations largely come from where this machine comes from. A robotic arm has a very specific history and a very specific application that it was initially developed for. And beyond the obvious limitations of scale and reach, we also have to deal, as designers working with these, we have to also deal with limitations of cost and accessibility, but also limitations of kind of knowledge accessibility and the learning curve that these types of machines require. And also, of course, some of the histories and the meanings that these types of devices bring into our own practice, even if we don't intend them to. So with my own personal practice, I would suggest that we rethink our relationship with robotics in architecture and robotics in design, and kind of move away from this iconic symbol of a robotic arm or an industrial robotic arm, and think about ways that we as designers can actively participate in the development of new robotic tools. And that is exactly the practice that I refer to as designing with machines. And when I say with, I'm kind of nodding to Donna Haraway's meaning of the word with, where I'm not only designing the objects that machines are producing, but I'm also designing the machine itself. And through the process of designing the machine itself, I get into new different design spaces that weren't necessarily obvious to me before kind of engaging with this particular process. So yeah, this work started for me back when I was studying at the iTech master's program, and we were very involved in working with industrial robotic arms. And I started thinking for the first time about all of these limitations that the robotic arms are bringing, even though I was and continue to be fascinated by these crazy, incredible tools. So my practice centers around designing mobile machines that oftentimes fabricate with filament materials. I, of course, also teach. And generally where I'm going with both this lecture and generally my research and teaching practice is trying to figure out scenarios where designing an object, designing a process for making the object, and designing the machine that is executing the process all become part of one continuous design cycle, where you kind of have to wear multiple hats, where you have to switch between these different design tasks and design processes. And most importantly, build interdependencies between different parameters. For instance, your geometry parameters in the object, and then something like motor torque parameters in your machine. And through engaging with and really tracing all of these interdependencies, hopefully create processes that we haven't really seen before, and that potentially would change the way we perceive robotics and generally design practices. And this is where I'm wrapping up my introduction part, and I'm going to ask our lovely hosts to launch the first vote. So with this vote, if I'm not wrong, you get to pick between not entirely all of these snippets because Zoom has weird limitations on voting, but you can pick between 2, 5, 6, 2, 3, 4, 5, 6, 11, and 12. And I'm going to wait for, I get to vote too. That's exciting.
So what are the choices, 2 and 11, or do we have more choices?
Well, we have 2, 3, 4, 5, 6, 11, and 12. So we're kind of taking the right-hand side and leaving that for a bit later.
All right. Oh, I cannot vote.
You cannot, but I can.
Can someone vote 11 on my behalf, please?
Fine.
Thank you.
Don't skew the voting. Okay, so as we are waiting for the results, I'm going to be ready to switch to the part that I need to switch to. Somebody's going to have to tell me what the result was because I don't really see it on my screen.
So we have almost 80%. So I think I'm going to call it. I'm going to rig this election. Yeah, 42 people voted, and these are the results.
I still don't see them. You're going to have to tell me the number.
That was my fault. Yes, there you go.
Oh, cool. Number 3 seems like it wins. Okay.
Mm-hmm.
Didn't expect that, but sure, let's do that. So this project is kind of interestingly places us at the very beginning of my personal career in robotics and computational design back in 2014. Where I was working within a large group of students on this ICD-ITK research pavilion that was centering around robotic fabrication with carbon and inflatable formwork. So this project is generally part of a larger body of work that is focusing on these types of materials and specifically investigating ways in which we can reduce formwork that is oftentimes necessary for working with these types of materials and for creating complex shapes with these types of materials. For instance, in the aerospace industry, every single component that is made of carbon and or glass fiber requires a solid mold, which is very expensive to produce and takes a lot of time and takes a lot of effort. Of course, in architecture, where we don't necessarily have the same needs, where we need to produce the same object over and over and over again, but we rather prefer producing more unique and individually shaped pieces and components. This idea of a formwork doesn't really work, neither economically nor in terms of time. So the goal of this project was to think about ways of removing the formwork and thinking about new types of formwork. So the project started with an investigation of a biological role model. And the biological role model in this case was a water spider, which is both one of my favorite creatures and probably one of the most ridiculous creatures that I'm aware of. So it's a spider that lives underwater. It's a horrible swimmer. It's actually pretty funny to watch it swim. I highly recommend checking it out on YouTube. But what's really interesting about this spider is that while it lives underwater, it needs some sort of air space to operate within. So it builds these very intricate underwater air bubble containers by kind of swimming up to the surface, grabbing a little bit of air onto its like super hairy body that is designed, let's say, in order to pick up air bubbles. And then it creates this sheet of web under the water, puts the bubbles underneath it. And once that bubble is large enough, it goes inside of it and starts to reinforce this little space from the inside in order to create the perfect shape for itself to basically sit in and wait for the prey to swim by. So we looked at this process and inspired by it, we've developed kind of an architectural version of that, or rather an architectural abstraction of this construction sequence, if you will. So what we came up with was an inflatable soft pneumatic membrane that served as a formwork for our final pavilion shape. Inside of this pneumatic framework, we have a robotic arm that sits inside and can reach every single point on the membrane. And the robotic arm is equipped with a custom designed end effector that actually lays pre-impregnated carbon fiber onto the surface of the membrane. And throughout that process, as the pre-impregnated carbon cures, you eventually get a pretty solid, stiff shell So once the shell is thick enough and stiff enough, you can actually remove the air pressure. You can cut out the entrances into the pavilion space. You can remove the robot, and you're left with not only kind of an interesting object in terms of architectural expression, but also something that is weatherproof, because the membrane that served as a formwork in the first construction stage remains within the piece and now serves as a weather protection device. So the design process for this project started with picking a robot and figuring out what types of different membrane shapes we can afford within the robotic reach, within the envelope of the robotic reach. And what was important here is not only to simply calculate how far the robot can go, but also figure out which types of geometries will work with a robot moving continuously from one side of the membrane to the other, because that is not entirely a straightforward process. Once the shape was decided, it was then processed through FEA analysis to figure out in which spots along this shape that we have designed it would make most sense to lay carbon fiber, because carbon fiber, as you might know, is not the most cheap and also not the most eco-friendly material. So you want to use minimal amounts to achieve the maximum force distribution throughout your membrane. So that FEA then was used to generate a vector field, and the vector field was then used to run an agent-based simulation where there was a single agent that could travel anywhere in the membrane, and the direction of its travel was basically decided by the vector field. So in that way, we could generate a wide range of patterns that would respond to the FEA analysis. So in a sense, while the agent-based calculation is actually happening on a computer prior to the fabrication process, but in a sense, you can think about the robot itself being an agent and kind of operating within this agent-based space and then delivering a whole bunch of different patterns. And actually for developing the pattern, we had to run many instances of this agent-based form finding tool. And each instance had its own different set of rules. So for instance, there was one layer within the pavilion that were the primary beams, as we call them, that carry most of the load. There was another layer that was aiming to be the most distributed to kind of make sure that the membrane doesn't sag in any particular spot. There was another layer that was working on the reinforcing of the entrance areas, etc. So every single layer had to correspond with its own function, also had to correspond with the general force distribution within the membrane, and of course had to inherently correspond with the limitations of the robotic arm and how far it can reach, and in what continuous or not continuous choreographies it can reach different points. My personal kind of responsibility on this project was actually developing the custom end effector. So what we ended up doing is we've looked at a bunch of different fiber laying end effectors that exist in the field. And we realized very quickly that we had to develop our own from scratch, because laying fibers on a soft membrane is actually a very hard task. Because the membrane you have to always be careful about not puncturing it by pushing too hard on it, but you also have to make sure that you're pushing with a specific force to make sure that the fiber actually sticks. So in order to develop that, we basically had a continuous sensor feedback from the end effector that had a load cell installed on it. And that sensor feedback was fed back into the robot path planning. So when you start the fabrication process of a single layer, you already know your general path along the membrane. But as you go through that path, the robot continuously adjusted its z-axis value. So z-axis in relationship to the end effector. So while it was still traveling along a predefined path, it could go a little bit in and a little bit further out from the membrane. Because of course, a pneumatic membrane is something that is not very reliable in terms of its geometry. Like once the air pressure drops because somebody walked in or something like that, you always have to very quickly adapt and be very dynamic about it. So though the development process generally consisted through multiple iterations of rerunning the agent-based system. So we actually, every day we were fabricating, we learned something new. And then our computational design team had to rerun the simulation over and over again to generate new patterns. So something that was really interesting about this project, that actually the final pattern design really evolved throughout the fabrication process. And of course, it is pretty stunning how thin the final product is while still being very reliable and supporting quite a large volume that is occupiable. And also kind of demonstrates a new type of aesthetic that we probably haven't necessarily seen applied to an architectural scale object before, that really just emerged from the parameters that we started with, being the robotic arm and the materials that we were using. And that project also for me was the beginning of my personal practice, where through building this end effector, I've really realized that even though my background is in architecture, I was never trained as a roboticist or as a mechanical engineer, but it was really interesting to realize how certain skills and certain kind of approaches to design allowed me to be better at building machines. And then from then on, I was obsessed with building machines. I saw a poll come up, and I think that was great.
Sorry, that was me. Can we do it again?
Yes.
All right. Let me relaunch this.
Sweet. Thank you. Oh, I guess I'm also supposed to vote.
So the membrane that you use as inverse scaffolding, was that the same membrane that remained after the construction?
Yes. And that was a big part of it, that we didn't want to waste any of the formwork. So the formwork then becomes the actual weather protection layer for the final building.
Wonderful. All right, we have 40 people, so I think I'm going to call it. And there you go. I believe we is number 5.
Oh, wow, that's cool. Okay, number 5. Oh no, I have awful news for you. I think my PowerPoint decided to save and is now not responding.
Are you telling us you don't want to talk about number 5?
I really want to talk about number 5. That's one of my favorites. I mean, they're all, I love them all. But this PowerPoint situation is kind of annoying. Technology, it fails us. That's why we need to build our own technology.
Exactly. Well, maybe while PowerPoint goes responsive again, we can do like a quick Q&A. If anybody has a question, feel free to unmute yourself and jump in, maybe.
That'd be great. I think I might have to restart this. I'm just going to quickly stop sharing for a second.
Hi, Maria. I have a quick question. How do you stick the fiber onto the membrane? Am I missing that part?
That's actually a really good question. So the membrane that we're using in terms of the material is actually ETFE membrane, which is literally designed to not be sticky to anything, because that's oftentimes what they use in facades. So in order to keep it clean, you actually want to design it in a way that it doesn't attract anything. But basically what we did is there was a little kind of spray gun on the end effector that would spray glue that we managed to find that is kind of an existing product and is a specific type of glue that they oftentimes actually use for carbon fiber and glass fiber fabrication in aerospace, and they spray it onto the formwork. And the special thing about this glue is that it allows, like it is very sticky when it's wet, but then once it dries and once the fiber cures, the stickiness kind of goes away. So in the end, the final object actually doesn't really rely on that glue connection, but really relies on the geometry, like the position of the membrane, because it's kind of tensioned already against the fibers that are cured, and nothing can really go anywhere because it's just there. Okay, I'm trying to relaunch my PowerPoint. In the meantime, if we have more questions, I'm happy to answer.
Hey, Maria, was there any troubleshoot process that you were anticipating? For example, if there was any puncture on the ETFE membrane, ways to fix it or ways to patch it in a way that, one of the limitations that I see in computation design is that we always think of it as a whole and we don't think about like where it goes off and then how we can fix it partially. So was there any anticipation in that process that you wanted to?
There was definitely, well, funny enough, we've never had to patch the membrane because the robot punctured it, but there were more than one instance of humans showing up at night and kind of like sticking knives through the membrane, which is really weird if you ask me. So yeah, basically it's the same patching process as any other really membrane patch. Like you just attach a little piece of material and use the glue to patch it. I mean, we were very lucky that all of the patches that we had to do, a lot of them were in the entrance areas that in the end ended up being cut out anyways. But some were, I mean, the patching was not super visible, but like if you knew where to look, you would probably find it. Sorry, I'm almost there.
I just want to let you know that our YouTube audience is starting a small coup and they want to extend the lecture so that you cover everything. Just...
Oh, geez. I mean, you could.
I'm not going to ask you to do that, but it's your choice.
Well, I feel like I'm guilty for not cleaning up my hard drive, and now I'm hitting all of these technical problems.
It's okay, take your time.
Okay, I think we're almost there. We're almost there. Yes. Pew. And I need to switch my displays. Oh my God, we're back. Almost. Give me a tiny second to share it again. And let's hope this goes better. So what was the result of that vote again? 5, right?
5, yes.
What is 5? Sorry, I have to look this up. 5 is Morphous 1. Awesome. Okay. So this is what is kind of exciting and also really weird about this particular lecture format is that because we've skipped 2, we have chunks now, but I think that's great. So this is a project that I worked on in my kind of personal research development. So this was not, if the previous project was a large team project, this was kind of just me and a couple of student assistants. And this project started with me being very fortunate to have an opportunity to show my work at the Milan Design Week a few years ago, where they basically provided me with a nice space and also provided me with an opportunity to do whatever I wanted to do. So the space itself, it was a super large exhibition space and it had these 2 walls that were opposite each other. And my goal was to create a filament wound structure in between those 2 walls. And in my work prior to this project, I've already been working on developing wall climbing robots that actually manipulate filament types of material in order to create tensile structures. But here, because the 2 walls are separate from each other, I had to begin to think about not only the machine that can operate on the wall and anchor the filament to the wall or to pre-installed anchors in the wall, but I had to extend my kind of taxonomy of robotic creatures. And that's where I began to think about different types of robots working together in order to actually create a fabrication system that is still pretty simple in terms of degrees of freedom of each separate machine, but becomes quite complex and provides a really nice and volumetric design space through this collaboration between multiple machines. So this final robotic system that I've developed for this project consisted of 2 wall climbing machines. Each of them can stick to a wall. It can drive anywhere along the wall. So it's kind of like a 2 degrees of freedom machine that relies on the environment that you place it in order to kind of define its work envelope. And then the second type of machine here was this shuttle robot or thread walker. It has acquired multiple different names throughout its life. But basically that robot only travels along a single thread of filament. And in this case, that was actually just cable. And by traveling in between the 2 walls, it carries a bobbin of filament material. As you can see in this image, there's this tiny little box where the actual filament sits inside. And by traveling between the two wall climbers, this thread walker or this shuttle actually passes the material from one side to another and allows the fabrication space to really extend from these two flat surfaces into the whole volume between them. So these are some of the videos of the actual fabrication process. And I don't know if I'm optimizing for screen sharing anymore because I forgot, but I hope this is playing well. So as you can see here, the shuttle robot arrives at one of the walls, passes the filament cartridge to one of the wall climbers. The wall climber that has a special end effector that allows it to anchor filament around these pre-installed anchors goes and finds the correct anchor in a sequence of anchors, does the whole anchoring routine or the connecting routine, comes back to the shuttle, passes the bobbin back to the shuttle goes back, and then through iteratively performing these same three operations of anchoring, passing, and then moving from one wall to the other, the overall system can produce a pretty extensive tensile filament structure using some of the principles of cordless filament winding. And what cordless filament winding means is basically a method for sequentially connecting multiple points with this soft filament in a pattern that will result in a double curved structure. So first you connect, for example, if you have two circles on two sides, first you connect point 0 to point 0, then point 1 to point 1, etc., to kind of create a cylinder. And then for the second layer, you do the same, but you offset the sequence, the pattern a little bit. So in the second layer, you create point 0 to point 1, point 1 to point 2. So there's a little bit of a twist. And as you layer these multiple twists over each other, you eventually get this really nice doubly curved surface that actually works. And of course, for me, this project is very much a demonstration of the idea of A, mobile robots in architecture, and B, custom designed robots in architecture. And you can really see the kind of radical difference in scale between the object that the robots are producing and the scale of the machine itself. The machine is pretty small. I actually have some around I can show you later. And also I guess the most interesting part in this project is, again, what I've just mentioned, that each machine has a very small and a very simple work envelope, which means that the machine itself is reasonably simple, which means that the control sequence for this machine is reasonably simple because you only need to navigate in a 2D space. But once you connect these two 2D spaces with a third space, with the singular linear workspace, you suddenly get the overall work envelope of the whole system, which not only is pretty extensive, but also if you imagine deploying the same system in different interior spaces, by kind of its nature, this workspace will adjust to any space that you place it in. So for instance, I can deploy the same system in this room and then fabricate something that is really small. And I can also deploy the same system in a way larger space, granted that some adjustments need to be made to the cartridge, and create a way larger object. So the system is scalable, but scalable in both directions, which I think is something that I at least care for deeply. So that was Morphus 2, and it's voting time again.
Woohoo, let's do it.
Maria, how did
Yes.
bot wrap the filament around it? I saw that it had the end effector and sort of did a 360, but I'm a little more curious as to the specifics of that mechanism.
Sure, let me quickly pull up that slide for you. It lives in a different slide deck, so that's why. Where is it? There we go. Assuming our PowerPoint doesn't betray us again. So the two machines can, like this is a different project, I'm kind of again jumping. But the two machines can pass this bobbin from one machine to the other. The reason why I'm showing you this because that's one video. And this is actually the close-up of the end effector. So it's basically a ring that is also a gear, and it has a slit in it. So as you approach an anchor, you can rotate your whole bobbin around the anchor without really letting go of it. And the bobbin is held by electromagnets onto the end effector.
Thank you.
How do you
Mm-hmm.
how do you control like the tension of the bobbin and the thread? Because that's got to be something, no?
It's tricky, and the honest answer is that I don't, or at least not in this particular project. There is, in the last project, I've had a separate tensioning system that was actually controlling the filament tension. But yeah, tension control is a super hard problem to solve, and kind of a very not as straightforward as one might think. So for this particular project, I was kind of relying on I had a little subroutine for the wall climber. Whenever it would do the anchoring, it would then drive straight down first. And that helped to pull the filament a little bit around the anchor. But generally, we've done a lot of post-tensioning manually. Basically, what we did is we took those anchors, because the anchors are actually bolts with the custom designed kind of hook attached to the bolt. And then after the fabrication process was done, we kind of just screwed the bolts a little bit deeper into the wall so that the whole thing post-tensions itself.
Wonderful, thank you. Well, I'm going to call the vote to an end, and there's a tie. So I guess, Maria, you have the last call on this one. Between 6 and 8.
Between which and which?
6 and 8.
6 and 8.
Yes, with 11 being very, very close in the polls.
Oh, this is tricky because I myself voted for 8. So I feel like it's unfair for me to actually call it. Well, you're not voting. How about you call the...
I would vote for 11, making it a triple tie. So
you're not helping.
I guess we can. I would say let's continue with the natural succession and do number 6, perhaps.
Okay, cool. I'm gonna make that fast because it's quite similar to quite similar to the previous project, but also it builds upon it quite a lot. So after wrapping up the previous project that I just showed you, I was kind of trying to think about it critically and also investigate, think about the different parameters that I would have done differently. And one of the big issues with that project was, on the one hand, there was a problem of idle time. So the whole process took a long time, mostly, I don't mind processes taking a long time, but it was kind of painful to watch every one of the wall climbers sitting there for more than half of its operational time, simply waiting for the other side to actually finish its job. So there was a lot of moments of just waiting. If you look at a single machine's working time, more than half of its time it's spent just waiting. So somewhat an obvious and I guess intuitive solution for that was to add more shuttle robots to the game. And then the other question, or the other problem that I was excited to solve, was the fact that this vacuum wall climbing robot, because it's based on negative pressure in order to stick to the wall, it requires a lot of energy to actually operate. So as you've probably noticed in the videos, every one of the wall climbers is a tethered robot. So it has a cable running to it. And because it has a cable running to it, the workspace is actually not entirely free. So for instance, once you place this curve of anchors, you're inherently constricting the robot from entering inside of that curve. Because once you pass in between two different anchors, you're kind of in danger of entangling the cable around the anchor. And then, that's it. You have to come in and manually fix it. So another thing that happened with this project, besides adding another shuttle, is I've developed a new climbing locomotion system that took away all of the vacuum stuff. And this locomotion system relied solely on arrays of magnets. And it wasn't able to climb on walls. Well, it could have climbed on metal walls, but it was designed to climb on relatively thin sheets of material. And the idea here was, eventually the project was tested on 5 millimeter thick polycarbonate transparent sheets. But the idea here is to think about potentially upgrading the system to be able to operate on materials like facade panels, to even operate on windows, like on the glass panels of a window. And generally, sheet materials are pretty common in any architectural space. So kind of extending not only the taxonomy of robots, but also extending the taxonomy of different environments where these custom machines can be deployed. So here you can see how the robot works. It kind of, it has a structure of a sandwich, I guess one can say. So it's made of 2 parts. And then the material you're locomoting on is your ham or cheese, so depends on what sandwiches you like. So you take these 2 parts of robot, you clamp it onto a surface, and then you give it the bobbin or the cartridge and there you go. And what is very special about this system is it takes very little energy for the robot to actually stay on the surface, because all of that work is actually done by the permanent magnets. So you're only using your battery life while you're actively moving. If you're not moving, you're just sitting there waiting for your server to dispatch commands. And another part that was interesting about this project is the tracking system. That in the previous case, there was a set of cameras looking at the robot body, and the robot body had a pair of visual markers on it. So as you fabricated more and more, you got more and more situations of obstruction of your visual markers, which made a fabrication process really difficult at later stages, especially when you had to attach your filament at the bottom of the anchoring curve. So here, because of the sandwich kind of topology of this robot, I could attach the tracking markers on the outside of my work envelope, because I'm operating on these thin sheets of plastic that are suspended in the space. So my tracking system is outside of the workspace, so I'm minimizing the problem of obstructing the actual marker within the fabrication space. So here you can see some of the snippets of how the actual fabrication process worked. The passing system is very similar. It also works on based on electropermanent magnets, which are absolutely magical devices. Electropermanent magnets are the best. And then as one shuttle robot approaches and it leaves for the other robot, the second one arrives because it just came back from the other wall or the other side. So the fabrication process for each machine is almost continuous. And of course, what was quite special about this is that the whole anchoring end effector could be fully eliminated, because the robot, since it's now tetherless, so it doesn't have a power cable dragging behind it, it can actually just drive around the anchor in order to attach the filament, instead of having this whole secondary system with an extra motor and extra complexity, of course. So the goal, as usual, I guess, at least in my work, is to reduce complexity of the machines and of the control system while maximizing the complexity of the work envelope and what these machines can do. So again, there's a very similar diagram to the previous project of thinking about individual machine work envelopes, like these two 2D planes and these two linear spaces with tiny little overlaps at the points where the robots pass the material to each other, resulting in a pretty extensive volume of the work envelope. And of course, because the machine in this case is tetherless, there were all of these opportunities to actually design the pattern of the final object by driving between anchors selectively. So the final piece was this array of lines, semi-straight lines that, of course, the tension problems came in. But this would not be possible to fabricate with a tethered machine. And it's voting time again.
Woohoo, let's do it. We have a hard stop at 11:30, and I would like to leave some time for questions and discussion. So I estimate perhaps we can do a couple more of these passages. How does that sound?
Mm-hmm. Sounds great. I mean, I'm easy. You tell me when to stop.
Well, if that was me, it would not stop all day, but we have infrastructure limitations. Oh, well. 11 is also almost winning, but not quite. I know, and people on YouTube want 11. Let's see.
I mean, you're the host. You get to overrule.
But I don't want to do that. I'm very sensitive with voting matters these days, you know?
Aren't we all? That is very true.
Yes. So I'm just going to encourage everyone to vote. There's still 10 people. Yuho, please. Yuho? Oh, maybe that was a mistake. All right. Oh, we have a tie.
Exciting.
All right. So I'm going to give 10 more seconds in case we can untie. Otherwise, all right. And I'm just going to end polling. And we have a tie between number 8 and number 11.
Okay. So a piece of information that you don't have that I think is important is also 11 is way longer than 8.
Up to you.
Which-
The YouTube chat is clearly voting for 11.
Okay, fine. Let's do 11. Okay, let me quickly pull that up. So, oh, I'm now realizing that this is a wrong slide deck. Isn't that fun? It is fun. Let me see if I can actually fix that quickly, because this is outdated.
Are we saying
And
11
less
is
fun.
jinxed?
Huh?
11 is jinxed, right?
11 is slightly, well, it's even longer. That's basically the problem. But let me see if I can be fast in fixing it. I was wondering, I was like, I thought I changed the, seriously? Damn. That's annoying. Let me quickly look at this. No, you know what? It's fine. Great. Never mind. Wow, that's not what I meant. Okay, great. Ready. So this, an important disclosure. This is, I'm not a historian. I'm not a theory person. So what I wanted to share with you in this, now I feel like legendary 11 snippet, is basically some of the history that I personally really care about, and some of the history in the kind of world of machines and designers and machines and architecture that has informed the way I approach my personal work. And of course, there's no one way to think about machines and design practices. There's a lot of different ways to look at the history. So for instance, what you see on this slide is Mario Carpo's take, where he looks specifically at the history of calculation techniques and even the history of different numbering conventions, and then how tracing that all the way back to Alberti and looking at how that impacts not only ways we design, but also ways we build and the ways we use both the technologies that are available to us, but also kind of our own bodies and physical objects in order to design on the spot and to design in kind of the real world at full scale. And if you're curious about that particular approach, I highly encourage that you go and read When is Digital in Architecture, which is an amazing book and a collection of a whole wide range of approaches. Well, we're not going to take Mario Carpo's take on this. We're also not going to take John Harwood's approach, even though it's also exceptionally interesting. And again, I highly recommend this book. So John Harwood has been for quite a bit, has been tracing the history of relationships between designers and technology companies and the outcomes of multiple different types of collaborations, specifically focusing on the IBM. And there, of course, the outcomes vary from logos to buildings, to larger buildings, to different prototypes, etc. I personally really like to think about this history from this point in time because it's also almost impossible to actually think about the relationship between machines and design practices without looking at that field around 1960s, and specifically the design tools that were developed by interdisciplinary teams of computer scientists and designers. And one of the first examples of these design tools is, of course, Ivan Sutherland's Sketchpad that was part of his PhD thesis, which is basically a computer program for designing. It's both a computer program and a set of hardware tools for CAD. And really the Sketchpad is the earliest, it's kind of the grandparent of the CAD tools that we use today. From the slightly different perspective, beyond Ivan Sutherland's Sketchpad, another kind of chunk of information, chunk of history that is almost impossible to avoid when talking about the relationship between machines and designers and machines and architects is, of course, the general field of cybernetics that roughly began, or the beginning of cybernetics as a field can be traced to early 1940s that started at the early Macy conferences that later were renamed into the cybernetic conferences. This is not a real photo. This is a piece by Susan Treister, which is kind of, it's actually a screenshot of her video. I'm totally sidetracking here, but her work is amazing. Go check it out. Some really great speculative history there. Back to real history. So one of the, I guess, heroes of cybernetics is, of course, Norbert Wiener, who actually defined the term and the term that really stuck around and kind of stayed there forever. And he defined what we now refer to as first order cybernetics, where he defined a system that has a goal, that aims towards that goal. And while it is affected by the environment, it corrects its actions to correct for the environmental interference, and then eventually achieves the goal. Some of the more details on this you can read in both the Macy Conferences collection book. It's super hard to read, but also super fascinating. And it's really interesting to look at the larger field of cybernetics, which was basically a whole bunch of people from different disciplines. There were some biology scientists, computer scientists, engineers, mechanical engineers, social sciences were present. And apparently a lot of the participants' recollections say that it was, while very productive, but also very hard, because every single person with their own background almost spoke a different language. And of course, when we say language here, we mean like the professional jargon and the way one approaches a specific scientific or research problem. And I think this is still very much the case. And I'm very curious to continue exploring that. Sorry, my headphones disconnected for a second. Another person to know and look into within the field of cybernetics is Ross Ashby. There's actually some really nice videos of him on YouTube explaining what cybernetics is in very simple words. But the reason why I personally care is Ross Ashby built the system that was called the Homeostat, which is one of the first systems that can be called fully adaptive. It's basically this array of these four boxes that each has a little needle that is connected, like electronically connected to the other three boxes. And for instance, if you bump one of them into vibration, the whole system comes to life, trying to get back into an equilibrium state. Not really going to go too far into detail on how that's done. I mean, by contemporary means, that's a pretty straightforward circuit, but it's fascinating. And apparently, Alan Turing was writing to Ross Ashby at the time because he read about the Homeostat, and he said something like, "But why are you building this physically? I am building this computer thing that I just came up with. Why don't I just do a simulation?" And then Ashby was like, "Nah, I'm good. I'm happy with my physical stuff," which is just, you know, this little anecdote, but also something that I can really relate to in terms of building physical machines versus building digital machines, because I'm very much a physical machine person. Anyhow, moving on, another super important person in the field of cybernetics, and I guess this is where I'm going to wrap up the cybernetics bit, is of course Margaret Mead, who published in, I believe, in 1968. She published a paper called titled "The Cybernetics of Cybernetics," where she basically coined, she didn't necessarily coin the term of second order cybernetics, but later on, what she proposed at that moment would be referred to as second order cybernetics. And basically, it's very similar to the initial definition, but it kind of wraps it in another layer of itself. So if you imagine this initial definition of a system that has a goal, and as the environment acts upon it, there are certain errors, and then the system has to be able to correct for the errors to still achieve this goal. So Margaret Mead's definition was, yes, it's that, but then there is another layer where the system, if not able to achieve the goal, it needs to also be able to set a new goal for itself, depending on the environment. And this secondary layer kind of takes the whole cybernetics question into a more critical space. So it kind of places the observer. One can think about these systems as a single system that resets the goal, but at the same time, the secondary layer can be seen as the observer of the system. So we're really including the observer and the designer within the definition of cybernetics as a whole, which from then on, you know, the whole approach became very, very different. I have a tiny sidetrack about Margaret Mead. She actually also played a critical role in influencing the sexual revolution in the 1960s. She's incredible. Read about her. She's the best. And while it is, of course, impossible to talk about the relationship between machines and design practices without looking at the early computational tools, early design tools, and some of the context of the cybernetics, it's also absolutely impossible to talk about this relationship without looking into early computational practices of artists, for instance, like Vera Molnar, who not only developed, who were also practicing around the 60s and not only developed their own algorithmic tools for generating the drawings and generating the actual artwork, but also executed them using CNC plotters, which arguably presents them as earliest instances of digital fabrication in a design or artistic practice. And while there are many, many ways of tracing the early digital art, and this could be its own 3-hour lecture, I'm just going to point you at a couple of important people and a couple of important kind of key figures. And the first one is Max Bernz, who was actually a professor of philosophy at the University of Stuttgart, where he curated what is agreed to be the first worldwide exhibition of digital art in 1965. And the exhibition was basically a collection of work by George Neese, who is one of the early digital artists. Apparently the exhibition wasn't very well received. The fancy Stuttgart crowd said, this is not art, this is fake, and nobody was impressed. But still, this is a super important time in both the history of art and also history of computational design, computational practices, algorithmic art, and digital fabrication, because George Neese was also actually using CNC plotters to output the final result of the algorithms that he was building. Max Bernz, along with Abraham Moles, also published a series of magazines, or a magazine, which I'm not sure how many editions there were in total, but it was quite a fundamental kind of piece of media. It was called Bit International 1. It's mostly in German, which is very annoying, but some of the archives of the magazine are available and searchable online. So again, if you're interested in computational art, go for it. Another super kind of rock star person that I want to draw your attention in this context of digital design, digital art, and digital fabrication is Josiah Reichardt, who not only published some amazing work on the role of computers and machines, but also curated the iconic exhibition titled Cybernetic Serendipity at the ICA in London in 1968. So much exciting stuff is happening in the 60s. The exhibition had an amazing soundtrack, and this is my sidetrack. Go check out the soundtrack. It's really, really good. But what matters in our context is that one of the exhibition pieces was Nicholas Schofer's sculpture CYSP1 that was originally developed in 1956 and apparently is considered the first cybernetic sculpture in art history. It is not only kinetic, but it's also responsive. So there's a bunch of light sensors inside of this piece, and the visitors were given flashlights that they could use in order to interact with it, and then the sculpture would respond. The exhibition also featured Gordon Pask, who, as you may or may not know, plays a very important role in kind of the development of the computational world and architecture. And the piece that was shown was the Colloquy of Mobiles, but my personal favorite piece from Gordon Pask is actually Musicolor, which is a digitally driven machine that the machine itself is very minimal. It's like this small disc with different colored films on it, but then the kind of brain that drives the machine is of course huge because that's the time of computers that take up a whole room. But basically the Musicolor works. Why I think this is really exciting and why I think this is actually maybe counterintuitively most architectural is it's a machine that can be placed in a space, but then by creating these arrays of colorful lights, it responds to sound. So it was initially designed as an accompaniment to an orchestra. So it responds to sounds and responds to music. But then what it creates a kind of layer upon an existing physical space. So it inherently works, it is inherently site specific because it only projects light to what you give it, the space that you give it. And it inherently engages with the space that you place it in, which for me is something that I find very important, both in terms of my own work and in terms of thinking about kind of reconfigurable spaces and architectural interventions that have to do with robotics. Later, Pask, of course, publishes the architectural relevance of cybernetics. a very, I guess, well-known article in the Architectural Design issue of September 1969, available online. Go and find it. Super interesting read. And then from the other perspective, when we think about the whole machine designer relationship, we cannot really skip all of the speculative work that happened. And just like with the previous examples, there's no good way to trace everything, and that would take its own lecture. But a couple examples that I would like to mention is Dennis Crompton from Archigram and his piece Computer City, where the metaphor of a computer is almost literally translated into a design and kind of a drawing of the city. Another piece from Archigram is, of course, the Walking City, which is one of my personal favorites, which is this vision of a very futuristic building as machine, building as this living creature. And the way they wrote about it, if you actually start kind of like reading deeper into the project, a big part of it was not only talking about the machine itself and like, what does it mean to live in a machine, but also think about how these types of machines would allow us to cross landscape and political boundaries. And what would that mean in terms of socio-political structures if our houses did not belong to a place anymore, but were these fully movable, kind of independent of borders, independent of different country structures. So it's super fascinating work. And of course, the very famous Plug-in City from Peter Cook, also Archigram, also 1964, because everything exciting apparently happened in 1964, which is this vision of a fully reconfigurable half machine, half building as well. And of course, the Plug-in City is largely, at least conceptually, connected to the Fun Palace project, which was developed by Cedric Price, John Littlewood, and Gordon Pask in collaboration. And it was an alternative project for theater that it was also fully reconfigurable. The difference between this one and the Archigram projects was that this one was actually designed to be built. Unfortunately, it didn't end up being built, but it was really, it wasn't speculative as much as the Archigram work. It was very much designed for a real site. It was designed for a real application and with a real client in mind. Similar to the Generator project, also by Cedric Price in collaboration with John and Julia Fraser, where the idea was to create this fully responsive architectural space that was made up of these little cubes. But the interesting part here is not necessarily the hardware, so not the, or at least for me, not the architectural shape itself and not even the way it's moved, but the way Cedric Price thought about interacting with the user. And this is where the boredom program comes in that I kind of mentioned in the beginning of the lecture. He envisioned an architectural space as really a partner and as something that you can have a dialogue with, and something that gets bored if you don't interact with it enough. He proposed a whole big list of different activities that people can actually do within this generator building structure. And some of them are more funny than others. I cannot now remember my favorite one, but some of them are really strange and kind of fun and provoking. And something that I find really interesting in these particular series of drawings of the generator that are some of the archival drawings that are available through the Canadian Centre of Architecture is the way the actual machine is depicted. I just really love this little piece of a crane in the corner, which I like to believe is intentional, because the physical machine is not actually the point in this project. The point is really the building that can think and that can make its own decisions. And finally, in relationship to this, I'm going to wrap up with the SEEK project from the Architecture Machine Group, initiated by Nicholas Negroponte. And the SEEK project had the reason why I kind of put these two together, and I'm not the only person who does that, is it has a very similar visual appearance, but a slightly different idea. So the SEEK project is this CNC robotic arm that can pick up bricks and arrange them in different places, which seems easy enough, sounds like a digital fabrication thing, except inside of the CNC machine, there's also a bunch of gerbils that co-occupy the space along with the robot and kind of wreak their own chaos within this architectural space. And this project was supposed to be a metaphor for this obsessively organizing robotic system that has its own logic and its own way of thinking and its own kind of set of rules in how it's arranging the blocks, but that set of rules allows it to somewhat respond to what the gerbils are doing. So the machine and the occupant, if we kind of metaphorically think of the gerbil as the occupant of the architectural space, they cannot really communicate directly, but they communicate through moving these blocks around. So if a gerbil knocks off a tower, the robot will know and it will go and try to put it back together. So they're in constant dialogue and there's this constant interaction between the machine and the occupant through the architecture itself. Unfortunately, the project was not very successful. Apparently, a couple of gerbils died, which is very sad. And they were also very stressed and kept on fighting with each other because they're not actually comfortable with like a bunch of people in an exhibition space with a machine hanging over them. But even though it wasn't necessarily successful in terms of its delivery, it is still a very iconic piece in the thinking about machines in architecture and machines in spaces and design. And this is where I'm going to wrap up because I feel like we're running out of time. Told you this is a long one.
Thank you very much, Maria. I think at this point, I'm going to call it, okay? And I would like, because we have about 15 minutes and I would like to open it up to Q&A, both from our Zoom call participants in the class and from people in our audience on YouTube on the chat. So I'm going to open it up to questions here while our audience on YouTube may want to post some questions and maybe I can relay them to you. I have a very small warming up question, if I may. This lecture and this invitation was in the context of the class that we teach, the Introduction to Computational Design. And obviously everything that you have shown today is like, it's a huge statement about the role of computation in being creative and making things. What would you advise a hypothetical group of people who are learning, who are new to computational design? What would you advise about how to go about it and what the potential of computational design might be for them? And from a beginner's perspective, what message may you want to give to them?
I think, and I'm not sure if this is good advice, but it's the advice that I keep on giving. Being a little bit insane is always a good idea in terms of like coming up with a crazy project and just going for it. I mean, that's how this whole robotic thing worked out for me. When I started my first wall climber project, a lot of people were like, that's never going to work. And I wasn't necessarily stubborn. I was just very excited because it was such an interesting problem to solve. So I guess find a project that really excites you and that you're willing to, spend time on without noticing how the time passes. And that's the best way to learn, through learning the parts of your work that you really love doing and just pushing on that.
I really love that. Can I further emphasize that?
Go for it.
Do not get obsessed with the technique or the technology of the platform. Think of goals and think of where to get with this, and then find the medium to get there. That is also, I very, very much relate to that message. Yes. I would like to open it up to questions. If anyone wants to participate, just please feel free to unmute yourself and jump in. Okay.
Love the awkward Zoom silence.
I know. We have some questions from the chat. Oliver 190519 is asking, you and I know about a bunch of Olivers. I wonder if it's one of them.
True.
Oliver is asking if that it seems like topology had quite a profound effect on some of the pavilions and some of the forms that you explored in your robotic 3D weaving installations. Was there ever an investigation into actual different topologies and their role, the potential role?
Are we talking about the environment, like the site?
I would assume we're talking about the actual shape of the surfaces that ended up being formed by the weaving. That's my assumption.
I'll take that. I think that the way I just misunderstood the question is also a very good symptom of how I approach my work. Basically, for me, every project starts with a site. Then there is kind of a simultaneous development of the robotic system that would work in a specific site, plus a fabrication sequence that would also work for the robotic system and the site. So for instance, when you remove the cable, you suddenly get this whole way larger range of different weaving patterns that you can achieve. And then the geometry of the final demonstrator piece really is a demonstrator of the design space. It's not necessarily, like, I don't necessarily put that much effort into that or that much time into that as a designer. And I guess that's also just shows the parts of my work that I'm most interested in doing and that I'm obsessed with, which is the robots and all the sequences and the communications. And then towards the end of every project, it's like, oh, right, we need to fabricate something. Quick, design something that works in this design space, but also demonstrates how this design space is special for this particular robotic system. So as much as I would love to pretend to be the architect who cares about the geometry, I'm not, which I think is fine, because the final goal is to collaborate with more people and hopefully find somebody who does care.
Wonderful.
I'm like, was that too honest? I don't know.
I like honest.
Awesome.
Andres Obregon from the chat is greeting you.
Familiar name.
Huh?
Familiar name. The iTech crowd.
I know. He is greeting you and he's asking you about your current life. How is your research life now in Canada? What is your current work there you're teaching? And I'm going to add to that question, what can we expect from future Maria Yablonina?
Oh, that's a tricky question. Well, Canada's great, I think. All I can really evaluate in lockdown is like the view out of my window. Toronto seems lovely. I haven't really explored. But generally, I'm currently working on a couple of research projects, some small, some large. I don't think I'm going to tell you that much more, but I'm definitely expanding I'm both moving away from the filament world, not necessarily moving away, but like adding to it. So I'm developing more robotic systems that are not necessarily fabrication only. So one side of my current investigation is thinking more about reconfigurability and spaces that respond. And I guess that's also what I'm hinting at in this history snippet, where I'm really interested in spaces, in robotic interventions in architecture that you can co-live with, that can not only fabricate, but also fabricate as a time piece, not necessarily as a final geometry. So it can, for example, if we're talking about winding, it can wind and then unwind and then wind something new, depending on both the programmatic change and the user behavior inside of the space. And then the other side of my current work has to do actually more with construction. So it's some robotic solutions for existing construction problems that have to do with surveying construction sites. And that's as far as I'm going to go with this answer.
Thank you.
It's fun. I promise it's fun. And I teach a lot.
I'm sure it will. I believe Marula from the call has a question, right?
Yes. Hi, Maria. Thank you so much for the amazing presentation. I have a question regarding interdisciplinarity of work, and what are the challenges or opportunities you find with working with different types of engineers? I can totally see how mechanical engineers can learn from the creativity of your process. And I was wondering, how do you find the collaboration with other types of engineers, for example, HCI people that are more kind of strict with regards to the outcome or the software? That's an open question. Yeah.
Thank you. That's an awesome question. And I think that's the question that we all need to be continuously asking ourselves in our practices. Well, the first point where I would like to start is that interdisciplinarity is super important, and we all need to thrive for that and kind of find new ways of establishing collaborations. In the work that I've been showing, I am also like a bit of an opposite to that statement. Very often I work alone, and that's just because that's how, I don't know, projects happen, funding happens, it's a lot of external parameters. I'm currently working collaboratively with a few people, which is super exciting. But generally, in my experience of kind of being, wearing multiple hats and being present in the architecture field, but also being present in the field of robotics and a little bit in the field of CS. I think something that we all need to acknowledge when establishing these collaborations is that every field and every personal background has its own constraints. Like besides, for instance, me wanting to work with you, I also have a certain academic or professional kind of goals and priorities that are important. And oftentimes what I see, for instance, in architects collaborating with CS background people is there's this kind of strange moment in time where you actually begin to approach people. So you've already figured out your project, you've already figured out what you're doing, and then you go to this computer scientist like, hey, can you solve this problem for me? And then the computer scientist responds, that's not an interesting problem. I'm like, this is so like, has been like, you're basically trying to hire a software engineer and paint it as a collaboration with a computer scientist, which is not how it works. And I think the real solution to that is figuring out how to start interdisciplinary collaborations earlier on, like basically creating both institutional infrastructures and kind of personal research infrastructures that allow multiple people from different disciplines to sit down at a table with literally an empty sheet of paper and figure out who wants, like, what are the problems that are interesting for each of the fields, and how can you bring all those interests together in a fully new project rather than kind of outsourcing the computational or the theoretical or sociology work to your collaborators.
That's a great way of viewing it, I feel, and it also creates new opportunities for learning from both sides. Absolutely. Or all sides. Yeah. Thank you.
Thank you, Maria. Well, the chat on YouTube just exploded with questions, and I think we only have like 5 minutes left. So I'm just going to. There's one about whether if any of your machines are open source, and whether if you ever imagine deploying them and observing how people use them and customize them.
They're not open source, which is not necessarily a conscious choice. It's a mix of my own anxiety of them not being good enough, and some imposter syndromes there. And I basically need to to start a separate project on just open sourcing all of the machines and all of the toolkits. Because currently, and that's a giant flaw that I also see very well in my practice, the machines that I make, I'm probably the only person who can run them because there are so many different bugs. And you just like when you're working with a 3D printer, you learn to know and you learn to love your particular printer. And then like, never print on the left top side of your build plate because it's like you learn all of these weird personalities in each machine. And that is, of course, even more so the case with these handmade machines because, well, they're handmade. They're not very precisely fabricated. I do my best, but still. But yeah, that is definitely something that I'm striving for and partially am getting to through my teaching. So I teach a machine building course in our undergrad program at the U of T, where we're focusing on each student or each group of students builds a machine, either kind of a serious fabrication machine, or my favorite part of that course is the useless machine assignment, where the students need to make something that works, like actually works the way they intended to, but doesn't make any sense. And that's always the most fun part of the semester when all the useless machines come in. But yeah, open source is a goal. I'm still getting there.
That would be great to bring as an assignment for this class too. The useless.
I can highly recommend. It's a great assignment.
Thank you, Maria. I actually relate a lot to those words, like because as a person who has written a lot of code that hopefully is used by other people, writing code for yourself, it's one thing, and writing code that is usable, understandable, and actionable by other people is a completely different beast.
Yeah.
Huge jump in development efforts, thinking about the cognitive aspects of your code. It's just a lot. It's a lot. I think at this point, we have a ton of questions on the chat. It's really unfortunate that we will not be able to cover them, but I think at this point, I'm going to call it. I would like to really, really thank you, Maria, for spending your morning with us, showing us your work, and giving us some insight about the processes behind them, I really loved it. And I see a ton of reactions on the screen as well right now. So thank you very much. Is there, if you want to say a few words or something?
Oh no, I should have planned for this, huh? Well, I guess when I give a non-voting lectures, I always end with what I kind of hope to see in our field is A, more interdisciplinary collaborations, B, more interdisciplinary collaborations between different types of machines. Something that I'm super curious about is actually taking these mobile machine techniques and putting them next to the industrial machines and then figuring out multi-species ecosystems of multiple robots that really extend each other's capacities and kind of help each other or like link the envelopes in a way that together they achieve something that is not really achievable by any single machine. So I want to see more of that, both with humans and with machines. And yeah, I'm really excited to see where this field goes and really excited to see more and more designers operating within this field, like being active participants, not just consumers of robotic technology, but active participants in development of new robotic technologies and like entirely new machines from scratch. Because I think that's what we've seen in the world of computational design for the longest time, like designers developing their own CAD tools, developing their own design algorithms and approaches. But we're only now beginning to see that happening with hardware rather than just software. And I'm super excited to see where that goes. And thank you all for having me.
Really like to see a lot of that. And thank you for being here with us today. All right.
Super exciting.
Thank you very much, everyone. That was it. Have a good day. Yeah. Bye-bye. Thank you, Maria.